In this video, we're going to look at calorimetry. Calorimetry is the science of measuring the heat of chemical reactions. Someone like a nutritionist might be interested in calorimetry, where they could use this science to determine the energy content in foods. A calorimeter is a device for doing calorimetry, and we see a crude calorimeter off to the right. What we have here is a source of fuel beneath the calorimeter, which when combusted will release heat into a sample of water. The basic premise this works on is that the heat, or the energy into the water, is going to be equal to the energy that's coming out of the fuel. I think you can see right away that this won't be entirely true, because there's a lot of heat loss off to the side. But for our purposes, at least initially, we're going to pretend that all of the energy coming out of the fuel is going into the water. Using our specific heat equation, mc delta T, if we know the energy that goes, if we know the mass of the water, the specific heat of the water, and the delta T of the water, we can then determine the Q into the water. That will tell us the Q out of the fuel, because those two Q's are equal to each other. If we know the energy out of the fuel, and we know the grams of fuel that are combusted, we get something called an energy density, or the energy released per gram of fuel combusted. And that's a valuable piece of information to have. What we're going to look at here now are 7 real quick problems dealing with calorimetry. The first reads, the specific heat of copper metal is 0.385 joules per gram per degree Celsius. How many joules of heat are necessary to raise the temperature of a 1.42 kilogram block of copper from 25 Celsius to 88.5 Celsius? This is just a specific heat problem to get you warmed up. So pause the video, take a minute, and solve this problem. Hopefully you got 29.0 kilojoules. For our next question, let's assume instead that all of the energy from question 1 went into 1.42 kilograms of water. By how much would the temperature of that body of water go up? And given the specific heat of water, and we're going to assume that the water stays in liquid phase for the entirety of this heating process. So this is a calorimetry problem because the Q out of the copper is the same Q into the water. So what we want to set up here is another specific heat question, where Q equals mc delta T. Here we know the Q, it's 29.0 kilojoules, so we're going to solve for delta T instead, Q over mc. Take a minute, and using the values for water, please solve for the change in temperature of the water. You can pause the video now. And hopefully you come up with a temperature change of 4.88 degrees Celsius. Now, let's combine these ideas. The question is, where did the energy for question 1 or question 2 come from? When methane burns or combusts, it releases 55.50 kilojoules of energy for every gram of methane that combusts. That's that energy density that we were talking about earlier. How many grams of methane would you need to burn to heat the sample of water from question 2? For this, we're going to assume all the energy from the methane combusting goes into the water. In question 2, that water absorbed a total of 29 kilojoules of energy. So I'm going to put that over 1, and multiply it by the energy density of methane, 55.50 grams, 55.50 kilojoules per 1 gram. Canceling out units of kilojoules gets me 0.52 grams. This tells me that 0.52 grams of methane would need to combust to supply 29 kilojoules of energy. By contrast, when propane combusts, it releases only 50.35 kilojoules per gram. How many grams of propane would need to combust to equal the energy of the methane in the previous problem? Well, that methane released 29 kilojoules, but here we're going to use propane's energy density of 50.35 kilojoules per gram. Right away you know this has got to be a larger number because it's less dense in energy. It's going to take more propane to provide the same amount of energy, and we find that indeed that's the case, that 0.58 grams of propane are required to create the same amount of energy as 0.52 grams of methane. So the question is, which fuel is denser in terms of energy content? Well, that's methane. Methane, CH4, is one of our densest fuels in terms of energy. Methane is the primary component of natural gas, which is one of the reasons that makes natural gas a really attractive fuel source. Pictured below is a typical lab calorimeter, just like we saw above. Fuel placed beneath the mass of water burns, and one can measure the change in temperature of the water, and because we know the mass and the specific heat of the water, we can then calculate the energy released by the fuel. However, as I mentioned before, that assumes all the heat from the fuel enters the calorimeter. Pause the video and think about some potential areas of heat loss in this setup. Maybe again you came up with some things like heat being lost out the side, heat being lost out the top, heat going into warming the beaker, potentially incomplete combustion. There's a variety of reasons why this might not be a perfect scenario, and there's certainly things we can do to improve our calorimetry setup. The final question in this video. Assume you build a calorimeter with 450 grams of water in it. You then place 2.5 grams of Swedish fish beneath the calorimeter and light them on fire. After they've burned completely, you notice the temperature of the calorimeter, that is the water, has gone up from 21.0 Celsius to 40.9 Celsius. If we assume all the energy from the burning fish went into the calorimeter, what's the heat of combustion, kilojoules per gram, released during combustion for Swedish fish? I think it's valuable to draw a quick diagram here. We have 450 grams of water, and here's our Swedish fish burning beneath the water. What we're concerned with here is that the Q into the water is going to be equal to the Q out of the fish. We know the mass of the fish, so if we know the Q, or the energy that came out of the fish, and we can divide by the mass, we'll get units of kilojoules per gram, which will be the energy density for those fish. So first, let's solve for the Q into the water. It's going to be Q equals mc delta T. Using our values for water, we know there's 450 grams of water times a specific heat of 4.184 joules per gram per degree Celsius times a change in temperature of 19.9 degrees Celsius. The math there says that going into the water, we're 37,468 joules. Using this equality that Q into the water equals Q out of the fish, we also know that Q out of the fish is minus 37,468 joules. Let's do a couple of quick conversions. Take that energy out of the fish in joules, convert it to kilojoules, then multiply by the mass of our fish. As units cancel here, you'll notice that our units of joules cancel, leaving us with kilojoules over grams. And that gives us a value, when rounded to sig figs, of 15 kilojoules per gram. Notice that Swedish fish, as delicious as they are, contain far less energy per gram than either methane or propane. Thanks for watching, and hopefully this video has given you a good understanding of the process of calorimetry.